All right, y'all. First thing we're going to be doing today is actually finishing where we left off last time. Okay, so I want you to grab your practice from last time, the check for understanding. Okay, it's at the front side of the second page. Okay, right where you see this information. And what I'm going to actually have you do is pause the video, and I want you to try problems number 1, and then flip it over and problem number 2, and then we'll go over those items. Okay, this is what we did in class to practice some of these ideas and review, because we will have a homework quiz over these topics next class. Okay, so this will help with that. Pause the video and try that now. Okay, if you recall, this C means complement, or everything except for. So this says everything except for 0, or that O means prefer the toilet paper to pull over the roll rather than under. So this is the probability that a randomly selected high school student does not prefer the toilet paper to pull over the roll. Okay, it's easier to talk about complements and just say not, because in this case, we could say instead of not over, we could say under, because that is the complement in this case. But there are options where there's not just 2 possibilities, and so the safest way is just use not, whatever the event you're looking at is. Okay. Now, I want to explain this part for a second. When we're asked to explain about probability, I always want you to include a part that says a randomly selected, whatever your context is, because it's really important when we're talking about this number. In this case, it was 23 over 58, and that looks like about 40%. It's not exactly, it's not one of those ones that comes out nicely, so I'm just going to roughly put it here. So I'm not saying there's a 40% chance that someone prefers to pull over the toilet paper on the roll. Okay, because y'all, they either prefer it or they don't. So it's 100% or 0%. Those are the only options. What I'm saying is, if I mix up everybody here and then randomly select one person, there is a 40% chance that that one person does not prefer to pull the toilet paper over the roll. Okay, so this randomly selected is super important for the true understanding of what this probability is measuring. Okay, hopefully you were okay with these don't add. They don't add because they're not mutually exclusive. Okay, students can prefer toilet paper over the roll and replace an empty roll at the same time. Anytime events can happen at the same time, they're not mutually exclusive. That just means there's an overlap. Okay, if you look at your picture, for an OR from a table, the only thing you want to do is just figure out where those 2 events exist. So the O is over the roll, that's these yeses. And then the R here is replace the toilet paper roll, so that's these ones. And then you just add up all those numbers. So you've got 70 and 24 more, so 94 over 116. Okay, there is a formula for this. I gave out a note card today. You'll have to come pick it up. Okay, but we talked about this formula last time. You can take the probability of the first thing plus the probability of the second thing. That's what this part was. But it's not equal to just that, because if you look at those numbers, they go over 116. We can't have a probability that's bigger than 1. So there's some portion that's being counted twice when we do that. That's this 58. Okay, it was in both this column and this row, so these individuals are counting it twice. We don't want to do that. Okay, and if it's in both, that's the probability of A intersect B. Okay, so that formula is your general addition rule. That's on your note card. I'm just going to have you, when you have a table, look at your table and do the probability that way. Okay, but I asked you to make a Venn diagram because we need practice with these. Venn diagrams are often helpful when calculating probabilities if you're not given a table. Okay, this one we just want to understand the relationship between the 2. Okay, the double yes goes in the middle. And then when I say replace the roll only, I mean I'm replacing the roll, but I'm not preferring over. Okay, so I'm still in this yes, but I'm not for the other one. So there's my 24. Same thing over here, the 12. And then the leftover is the double no, the neither to both of the events that I was working with. And then you were asked about does not replace the roll. This not means complement, so RC. And then and, we talked about last time, is intersection. So that upside down U looks like an N for intersect. And then prefers the toilet paper pull over, so that's your O. And then we want to find the probability of that. So same way we did the other one, I'm going to recommend you just look at your table. Okay, so if we're looking at our table here, our complement, okay, means we're not replacing. So when we look at the replacing, we're saying no, so we're right here. And then from those ones, we want also to be over, preferring over, so that's these ones. Okay, the difference here is this is an intersection, and so we're only looking for the overlap, and that's that number 12 out of the total. We can do the same thing over here with a Venn diagram, and I'm going to show you this, and we're also going to practice a new example of kind of a situation where you would want to use a Venn diagram instead of the table. But just for practice, when I say the complement of R, I mean that they are not replacing the role, which means I am somewhere outside of the replacing the role bubble. Okay, I could be out in the green space, or I could be in this blue bubble, but not in the middle. Okay, then when I am over the role, okay, over the role is this whole circle here. And when it's an and situation, I'm looking for the overlap. The overlap of my shaded region is in this moon shape here. So that'll be my answer, the 12. Okay, so you can do it either way. If you have a table, I think that's a little bit easier, but there are some benefits of a Venn diagram. Okay. Then you were asked to answer some questions based on this. Just a reminder that this bar right here means given, and that indicates that we have a total other than 300 that we're working with. Okay, so on this one, our total was 100 because we are looking only in 1976, meaning we are only focusing on this column right here. And since we're only focusing on that, when we look for the 4 plus children, we can only use that 40, okay, 0.4. And this says there's a 40% chance that a randomly selected, don't forget, randomly selected woman surveyed specifically in this year, this is given that they were surveyed in 1976, we're looking at the probability that that person has 4 plus children. Okay, so this is one way to write it. Another recommendation I have if you're struggling with your interpreting, just go see how other things are written just on other problems. And part B is a good example. It says, given that the chosen mother was not surveyed in 1976. So over here we would say, given that the chosen mother was selected in or surveyed in 1976, the probability that she has 4 or more is this. And then you put 40%. Okay, but this one was asking for not. Okay, so that's another complement. And you can just use S complement there. Those would be these guys on the right. And so there's a total of 100 for both. So we've got 200 on the bottom, putting them together. Same thing we're going to do for the second part C, the 4 plus children. We've got to take both of them and put them together to get 26, or 0.13. Okay, last one was talking about independence. I want to talk about logically first. Okay, the definition of independence means knowing that surveyed in 1976 happened will not make 4 more children less likely. It won't make it more likely. Okay, but if we look at our table, if we know that the mother is surveyed in 1976, the probability of 4 more children is 40 out of 100. If we compare that to 1994, it's 13 out of 100. If we compare that to 2014, it's 13 out of 100. Okay, or if we compare it to the total, it's 66 out of 300. And these are not equal. If they're not equal, then they cannot be independent. And we've got a formula that says that. So there were 2 versions of it that we talked about last time, and we talked about this first one mostly, but the second one is actually the one that makes sense in this context because we found those 2 items in the problem before. I want to really emphasize what this says. Okay, so all of these things have these C involved. Okay, and remember C stands for 4 plus children. So we're saying that the probability of 4 plus children, no matter what my total is, and if it's looking at the 1976, if it's looking at the not 1976, if it's looking at the total, meaning I don't restrict it at all of these things, if independent, should match. But if we're not independent, they won't be equal. Okay, so on your note card it says the probability of A, I think it says given first. So given B is equal to the probability of A given the complement and the probability of A itself. No matter what the total is, these should be equal if independent. So that's why I could circle all of these, and they'd all be equal if independent, because those are the different totals that are possible. Okay, but ours, if you look at those values, they weren't. Okay, we had 40 over 100 compared to 26 over 200. They don't match, they're not independent. Okay, if we know a mother was surveyed in 1976, it's more likely that she had 4+ children, because looking at our proportion, it's a higher proportion in that year. Okay. Next thing I want you to do is below where you have some space, I'm just going to scroll down here. I'm going to give you an example of a Venn diagram. That's actually a situation where it's useful. Okay, so we are going to use a two-way table if we have it, but if we don't have it, here's a question how that could look. Let's suppose in our class that the probability of being a dog owner is 60%. Okay, more than half of people in the class have dogs. And then let's say that the probability of being a cat owner is maybe a lot less, 10%. And then we can say people in the class who have dogs and cats take up 5%. Okay, drawing a Venn diagram for this can help us answer some questions, like what is the probability that excuse me, a person in the class has a dog or a cat. Okay, and here's how it looks. You're going to draw out your bubbles and label them. So you've got dog, cat. Okay, we know they overlap because of this last one. Remember, and the symbol for it is going to be intersection. So I want you to always start with that in the middle. And what I want to really emphasize with these Venn diagrams is that when I say dog, I mean this whole bubble is worth 60%. And if this whole bubble is worth 60% and 5 of it's here, that means there's 55% of students who have only dogs. They don't also have cats. Okay, then same thing goes for the cat section. 10% is this whole bubble, 5% of it's there, so there's 5% left over. And then there's always the possibility that we have people who don't have cats or dogs and they go outside. Okay, so I want you to find that real quick. Okay, here we've got 55, 60, 65, which means there's 35% left over to be out here. Last time when we were working with Venn diagrams, we just had flat numbers, but if the only information we're given is percentages, we're welcome to use percentages or decimals or fractions inside these Venn diagrams. So then if we want to find the probability of dog or cat, we're going to take all of dog, all of cat, and everything that's in a shaded region counts. So we just add those three up and we get 65%. We can also do this when complements are involved. So I'm going to go ahead and erase that shading. And now we're going to talk about the probability of maybe dog intersect cat complement. Okay, I want you to pause the video and try that one real quick. Draw on your Venn diagram, it will help. So dog is here. The complement of cat really means anything that's not in the cat bubble, which would mean all of this outside of the circle. If this is a union, like what we just did down here, we count everything in the shaded region. Okay, that would be 55, 5, and 35 all together. 95. But this is an and, which means I want where they overlap. So my shading overlaps only in this 55 section, which means that would be the percentage. That would be my answer. Okay, you are going to have a couple questions on your homework this time that review some Venn diagrams. So if you have any questions with that or struggle, please come see me. I'd be glad to help. Okay, the activity today we did in class was, can you get a pair of aces or a pair of kings? Assuming that we have 5 cards in a hand, 2 of them are aces and 3 of them are kings. And you're going to choose the first card, record it, and then choose the second card without replacement and record that. You're a winner if they're both kings or if they're both aces. So if you have a deck of cards, grab them and simulate this 10 times. Okay, if you don't, what I want you to do is just grab 5 slips of paper. Right, king, 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 ace, ace. And do that with those values. Okay, because I want to see this table filled in based on your simulation. Okay, so pause the video and take care of that for me, please. Okay, you should be able to answer this proportion out of 10, however many games that you had. Okay, we did this in groups, so we did it out of 20 or 30 if there were 2 or 3 people in your group. And then our group totals for the whole class, let's say there were 200 total games played, and maybe 78 of them were wins. Okay, so that looks like 39%. And what we want to talk about is, do we think that this 39%, or whatever percent you had there, is more accurate? Okay, we learned that the law of large numbers says if we increase the number of trials, we should get closer to the actual probability or the theoretical probability, but we still don't know what that theoretical probability is to know whether this 39% is very accurate or not. Okay, so one thing we could do is increase the number of trials. Instead of doing 200, we could repeat this 1,000 times. Not us, a computer simulation. Okay, but another is to step through a process to find the actual probability. And this one kind of deals with a conditional statement. And the method that we're going to use to kind of think this through is called a tree diagram. I'm going to work through this with you because it's the first time you've seen it. So what I want you to start out with is thinking about your ace game. So in your deck of cards, or hand of 5 cards, you have 3 kings and you have 2 aces. That's what we're starting with. Okay, and then we're going to draw a first card. And there are 2 options. Your first card could be an ace or it could be a king because those are the only choices that we have in our hand. Okay, so the first one, we're choosing the first card is an ace. So out of these, 2 of 5 of them are ace. Then the leftovers, 3 out of 5 are kings. Okay, but at this point, we've gotten rid of an ace going this way, or we've gotten rid of the king going this way. So we've got a new hand to talk about for each of these. Okay, so after our first one's an ace, we've taken this out, and we're left with king, 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 ace. And now we want to figure out the probability that the second card is an ace. So there's only one of those out of 4. And then the second card being a king would be 3 out of 4. And this is an or situation. We're doing one of these or the other. We can't have both the second card being an ace and the second card being a king. That's why these were still both out of 4. Okay, what I want you to do is do this one down here real quick. Okay, based on what the new hand would be after we take a king out. Okay, hopefully you got 2 out of 4. 2 out of 4. And if you call that 1/2, that's fine, but I actually prefer when doing these tree diagrams to leave them unreduced because it helps me see how these add together to be 1 throughout the process. Okay? And then the whole goal of this was to talk about the probability of each of the different possible outcomes. Okay, so we're going to take a pause real quick and list out the sample space. When we think about drawing 2 cards, there are only a few options that we can get, given that we started with 3 kings and 2 aces. Okay, we could have both aces. We could have an ace, then a king. We could have a king, then an ace. Or we could have a king, and then another king. And that's what these represent in our tree diagram, is the 4 possible outcomes. But we couldn't just calculate these with the probability with a sample space like we normally did, because an ace-ace is not as likely to happen as a king-king based on our original hand of cards with 3 kings and 2 aces. Okay, so anytime the outcomes in the sample space are not equally likely, you're going to have to draw out a visual for what's going on versus just saying, well, 2 out of 4 of them, the probability must be 1/2. Okay, it doesn't work that way. Here's how it does work. We have calculated the conditional probability here because we had, this was, say, our probability of an ace happening. Okay, and then this next one was the probability of another ace given that the first one was an ace. Here, this one was the probability of a king happening given that an ace happened, and so on. So the second one was a conditional probability. But and for us is going to mean multiply, okay, just like or meant add. And so our ace, the first one was 2/5, and the second one was conditional, but it was 1/4. And that gives me 1/10. I can do the same thing here, just following along. 2/5 then went to 3/4, so 2/5 times 3/4, and that's 3/10. Last little branch here, 3/5 times 2/4, which is 3/10, and 3/5 times 2/4 again. Okay, when you're doing this right, your sample space, including their relative probabilities, should always equal 1. And we've got 1/10, 3/10, 3/10, 3/10, which equals 1. Now, for what we're going to be doing, a lot of times decimals are going to make our life a little bit easier for some of these weird probabilities. So I'm going to go ahead and change these. We're over 10, so that makes it pretty easy. Remember, in general, when you're writing probabilities, you can do reduced fraction, decimals, or percents. And now the whole goal of this was to determine the theoretical probability of winning. So if we think about winning the game, that was the double ace or the double king. The double ace was here, or the double king was here. And remember, or is going to be add as long as they can't happen at the same time. In the game, you can't have 2 aces and 2 kings at the same time. So we just take our 0.1 plus our 0.3. And so our probability is 0.4. And if you remember, it's pretty close to the 39% that we got. Okay, what I want you to do is pause the video and think about how you would handle number 5. For this one, it's not quite the same as how we did conditional before, because a lot of times when we were given, we were just dealing with plain numbers. We don't have plain number of trials and theoretical probability. We can only see that in observed probabilities. Okay, so for this, we're going to use actually the probabilities that we see, not the flat numbers. Okay, but it's the same process as before. We want the probability that the first one's a king, okay, given that the person won the game. Okay, so remember, we're starting with the winners. Well, we just found the probability of winning the game was 0.4. Okay, but it's also this highlighted section. So what I'm going to have you do, if you don't have a highlighter handy, just write win on the top of these two. Okay, and that's our 0.4 that's going to go on the bottom. Now remember, with conditional probability, once you've restricted it down to a certain place, you can only use values in that restricted section. So I'm only focusing now on these 2 places. These ones don't matter. Okay, they're not of the winners. So now, of the winners, which of them had the first one being the king? Okay, and that would have been this one, the double king, so that's the 0.3. So then we have 0.3 over 0.4, which is 3 over 4, or 75%. I hope that probability is reasonable to you, because we think about this. It says, what's the probability that you had the first one being a king given that you're a winner? We know that there's only 2 ways to win, ace, ace, king, king, and we know that in the beginning there were more kings than aces. So it should make sense to you that it was more likely to win with a king than with an ace, and now we know just how much more likely. Okay, what we just did was called the general multiplication rule, but really it's this and situation. That and means multiply. What you have to pay attention for is deciding whether the events are independent or not. When we think about drawing a card, if I take my 5 cards and I draw out an ace, it's gone, which means this probability depends on what happened here. Okay, this 1/4 was not the same thing as this 2/4. Okay, these were not independent events. Okay, if you have a situation where that card was replaced, like you drew an ace, but then that ace was put back into the deck, then that would be a situation that was independent. When it's not independent, the second part has to consider what the first part happened. Okay, you find the probability of the first event, and then you find the probability of the second event, assuming that the first event already happened. And that's why a lot of times it's easier to use not reduced fractions, because those totals change. Okay? We're going to do some more examples with this next time just to practice kind of getting the idea of this. But what your homework has you do is it will tell you if things are independent, and then if they are independent, we don't have to worry about this. So let's look at how this changes just slightly when they are independent. It says the probability of A and B still, you're still multiplying, but y'all, if we remember, the definition of independent means that B is B no matter what the total is. Okay? In the situation here, the probability of ace was not the same thing 1/4 as it was in the original 2/5 because something changed. If they're independent, they will be the same. And then you don't have to worry about the conditional probability because it's just the probability of B. Okay. This is also a way to test for independence. If we're given the cat and dog situation that we practice, let me go back here. Events are independent if, went too far. Okay, if the probability of A times the probability of B is equal to the intersection. So here, if we wanted to test whether the probability of owning a dog or owning a cat were independent events, we just take our 0.6, probability of A, times our probability of B, which was 0.1. And then we compare it to the intersection, which was 0.05. Okay, when you multiply this, you get 0.06, and that's not equal to our intersection, so these would be dependent events. Because we assume that if you have a dog, you're probably more likely to also have a cat than just any owner, or maybe vice versa. Okay, but pet owners in general, if you have one, you're more likely to have more than one. So that may be playing a role, which is why these aren't independent. Okay, what you're asked to do on your check for understanding is just show that you can answer questions using a diagram. On your homework or on a quiz, I won't ever have you draw out a tree diagram. It's just a method that can help you come up with these and situations. You can also use the sample space. So what I mean by that is, if we go back here, if you can set up your sample space and you know ace is 2/5 times 1/4, you can find your probabilities that way as well. Okay, but for this one, we'll do a tree diagram. I'll help you with the basis of it. Okay, we're starting out with an election here. It says 30 states went to the Republican candidate and 20 states went to the Democratic candidate in the 2016 election. And then of those 30 states that went Republican, 29 of them were continental U.S., and the 20 states that went Democratic, 19 were in the continental U.S. So when we're setting this up, we're starting with our 50 U.S. states, and we're breaking them off into they either voted Republican or Democrat, and this is majority. And then within the Republican, we had continental, and then of course not continental. And this helps us show the possible outcomes. I could have Republican with continental. I could have Republican with non-continental. I could have Democrat with continental, or Democrat with non-continental. Your job is to find the different probabilities that go on the tree. Here, 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 and then based on those values, multiply for your final probability. Okay, pause the video, try that, and then you'll be able to check your answers. Okay, should have looked something like this, starting with 30 over 50, but after we've looked at Republicans, now we're only focusing on those 30. So 29 is what they told you, that means there's one left over. And then same thing on the Democrats, we were only having 20 of those states who went Democrat, and then 19 were given as Continental, so the leftover was 1. And then we just multiply those items to get our probabilities throughout. And remember, these must add to 1 when you're done. Okay, now that you have this, fix anything if you need to, but I want you to pause one more time to answer those last couple questions. All right, Continental and Republican, that was that first outcome, 29 over 50 or 58%. Okay, what we need to talk about is this next one. Okay, so don't worry about copying this down. We're gonna talk it out. Okay, because this one's a little bit tricky. So we're going to talk about choosing 4 states at random, which means we're really running through that probability tree diagram 4 times. Okay, so what I want you to do for this one is write out 1, 2, 3, 4. Okay, and we're going to think about the situation where at least one of these 4 that we just drew out is in the continental U.S. and went Republican. And right now, the only way that you are going to be able to do this is recognizing that at least one means all but none. Okay? And all but none means take 1, that's everybody, minus the probability of none. Okay? We're going to talk about other ways to do this down the road in a couple days, but for right now, this is the only method that what we've learned so far will help you with. Okay, so what we're going to do is talk about the probability of none. So for us, that means really the probability that they weren't U.S. Republican. So we need to find the probability of U.S. Republican and then just do the complement. Okay, so probability, continental, and Republican, we decided was the 0.58. So then the complement of that is just the leftovers, 0.42. So we want the first one to be not Republican or continental, and we want the second one to be not Republican and continental, and we want the next one to be that same thing all the way through. And since this is happening 4 times, the easiest way to do this is take my probability and just raise it to the 4th power. Okay, but this is still just the probability of none, so my final stage is just taking 1 minus that. And this is not a very nice number, so you toss it in your calculator, and then we're just going to round to a few decimal places. Okay, 3 or 4 is great. And that is your probability that at least 1. And a lot of times at least 1, because it's all but none, it's pretty likely. You're always going to see some pretty high probabilities here, because we're only leaving out one possible outcome. Okay. All right, this last one, given that a randomly selected state is not in the continental U.S., okay, so not in the continental U.S., if we go back to our tree diagram here, not continental is here, not continental is here. So we need to put those 2 together. That's 2 over 50. Okay, so here, I don't like using fractions very often. I prefer the decimal versions. Okay, so if we really quickly, this was 0.58, this is 0.02, this is 0.38, and this is 0.02. Okay, now we can work with those just a little bit easier. So here, if we put those together, it's 0.04. And then we want, from those, the highlighted section only, the Republicans. So of these, the Republican was this top one. So 1 out of 50 was our 0.02, which is the same thing as 2 over 4, or 1/2, 0.05. Okay, we treat it the same way that we did on the front side. Remember, we can have decimals and fractions because we're dealing with probabilities on our theoretical model. We don't have the flat numbers, otherwise we'd use them. Okay? Homework is on sapling. If you have any questions, like always, please come see me. We're going to try to practice a lot in class, but it's going to help you if, while you're doing your homework, you understand what's going on versus just clicking until you get the right answer with some feedback.